All right, you guys, today, fundamental theorem of line integrals. Whenever you hear the word fundamental, you definitely want to sit up and pay attention. This is really, it's sort of a cheat because it's really just a generalization of the fundamental theorem of calculus. So you'll see that when we prove this thing, it really just flows straight from the fundamental theorem of calculus. So today what we're going to do is discuss a certain kind of vector field. So we're going to continue to focus on these line integrals, in particular line integrals that compute work, and not just any kind of vector fields, but what we're going to call conservative vector fields. Conservative vector fields are the kinds of vector fields that you encounter in nature most often. For example, gravity is a conservative vector field. Electricity and magnetism, conservative vector fields. I don't know if all of the fundamental forces of nature are conservative, because there's the strong and the weak nuclear forces, and I don't know if they're conservative or not. I know they're weird, but that doesn't mean they're not conservative. Sounds like a political kind of discussion here. But anyway, so before I get into that, though, let's talk about homework. Are there any homework questions that you guys might have? Web work? Oh.
Will you go over web work 3? Because I've tried it like 8 times, and I read your email, and I read the book.
Still not getting it. Okay, that's fine. We can do that. For the longest time, this was remembering my password, and now it doesn't. It's kind of annoying. Now,
when you clicked on the 126.
Oh, there you go. Well, that definitely would help. Thank you. All right. Number 3, was it, Lila? Oh, yeah. Okay. I think it's always good to draw a picture when you're trying to understand one of these things. So first of all, this is something that I didn't talk a whole lot about on Wednesday, but you actually have to do 2 integrals here, which I may have outlined in the email, I don't remember, and then add the results together. So let's plot these points, 0, 0, negative 3, 4, and negative 3, 4, and negative 6, 0. So we have one here, what was it, negative 3, 4 here, and negative 6, 1, 2, 3, 4, 5, 6 down here. So there are 2 legs to this path. So the whole path is called C, but I'm going to break it up into C1 and C2. And it's also important to note how the path is traversed. So this path goes from 0, 0 up to negative 3, 4, and then back down to negative 6, 0. So that's the pictures that everybody should have on their paper, and I'm sure that you had no trouble with that. The next step that you have to go through, let me get, let's see here, let me get, is it negative 3 dy, negative 4 dx? Your numbers, of course, are going to vary. I've already forgotten. Yeah. And possibly, Lila, I'll keep going, but possibly you switch these, maybe?
I don't know. I've tried.
You've tried everything. Okay.
Yeah.
Let's walk through it. Yeah, there you go. So first of all, we have to parameterize the line segment from 0, 0 to negative 3, 4. And I refer you back to similar problems, I think, in Chapter 12. So I'm going to, just to sort of evoke what happened back there in Chapter 12, I'm going to call these 2 points P and Q. And the first thing I'm going to do is find the vector, the displacement vector, so that I can get the direction of the line. So that displacement vector is Q minus P. And that is negative 3, 4, big surprise. And to build the line now, I just take that thing, I'll call this R1 of t. I just take that thing and multiply it by t. And then I add a point on the line, which is, again, kind of pointless, but there it is. Whenever I write down a parameterization, I should also write down the range of t values for which this thing holds. In this case, for what t value am I at the beginning of C1? 0, exactly right. And then what t value gets me to the end? 1. But you do have to pay attention to that, because sometimes, like for example, if you are building this thing and you happen to do p minus q, then your parameterization values would be different. All right, let's do C2. So C2, let's call this capital R here. We'll do R minus Q. R is -6, 0, and Q is -3, 4. So it looks like we have -3 and -4. And so the parameterization of that part of the path, R2, is going to be t times -3, -4, plus any line on the curve. I'm going to use -3, 4, because that'll get my parameterization to work out nicely. So at what value of t am I at the start of C2? 0, good. And I'm at the end when t is 1. Why are those parameter values, those parameter ranges important? I need those for the limits of integration, ultimately. So it's really important that you pay attention to what those parameter values are. So here are the two parameterizations. Now I'm left with the task of computing the integral, which is the integral along C of -3 dy, -4 dx, which I've already noted I can write as C1 -3 dy minus 4 dx plus C2 -3 dy minus 4 dx. And I'll do one of these and I'll let you do the other one. So the integral C1 -3 dy minus 4 dx. The way to do this is to integrate from 0 to 1, -3. What is dy replaced by?
Are you doing the whole curve or just the first one?
I'm just doing the first part.
3, or is it 3, 4, 4?
Well, it's the derivative of this guy. It's the y coordinate. The derivative of the y coordinate of that guy. 4. Minus 4 times the derivative of the x coordinate. And I guess I should be a little more careful here. Let's put parentheses around that too. dt. Okay, so this is dy dt. This is dx dt. All right. And I think that's 0 in this case. You get the integral from 0 to 1 of 0 dt, which is 0. And presumably you can do the other one.
What I'm wondering is, if we're just trying to find the whole curve,
Yes.
the added one,
Yes.
and what I did, could you combine the whole curve, like, but you can tell what dy and dx are from the start, because across the whole curve, y doesn't change. Y goes from 0 to 0, and x goes from 0 to -6.
Oh, yeah, if you want to go that way, yeah.
And then you can just plug them.
Yeah. I think it's probably best at this stage of the game. It's great that you're trying to develop that intuition, and you're right, you can do that kind of thing. I think at this stage of the game, it's best for you to practice building a parameterization and plugging this stuff into the integral, because those are the skills that we're trying to develop. And then as you go along and you do those things, then you make these observations like Ethan has just mentioned. Okay, other questions about, yeah, Chris?
Number 4, the visualizing line integrals.
Oh, could have just gone
Yeah,
net.
most of them are just, I don't know.
Got it. Okay, remember the guiding principle here is when the curve is going with the force, that's positive work. When it's going against the force, it's negative work, and across the force is 0.
But it's asking whether the line integral is positive or negative, not the force, right? Not the work.
Well, this line integral essentially represents a work integral. So it's a path in a force field. Okay, so let's see here. This guy? Positive. Because these two legs are 0, right? And this leg is positive? Okay. This guy, okay, so this whole arc is 0. That's positive. 0, negative. What do you think? 0, because it looks like these arcs contribute nothing and these segments cancel. Let's keep going. The arcs again contribute nothing. Oh, sorry, the arcs now contribute stuff. The arcs are positive. Yep. And these are across, so what do you say? Yeah.
Wait, shouldn't the outside one be negative?
Oh, yeah, yeah. I'm not being careful here yet. This is negative. This is positive. Do you think this is more negative than this is positive? Yeah, it's a longer arc, and it's also swimming through bigger vectors. So yeah, negative. Thank you. This guy here. Yeah, it appears to be always perpendicular to the vector, so I would call that 0. This guy? I would agree with that. Because, what's your argument for positive?
Because the vectors in the upper segment are longer, so they're doing more work in that direction.
Yeah, so I'm getting positive work up here and negative work down here. There's a lot of symmetry here, but these vectors are bigger up here than they are down below. Good. The last one.
0.
Yeah, I think I agree. Why do you say 0?
Because at the top and the bottom they cancel out and the two sides. Because they're in opposite directions, equally as the.
Yeah, I like that.
Radially symmetric.
Okay. Yeah. Does that answer your question, Chris? Good. Other questions? One thing I have to remember to do on the next test is, you know, WebWork has lots of good picture kinds of problems. I need to throw some more of those on the exam. So, well, because I like these problems, you know, and they test some things that the straight up calculations don't test. So I do have to remember to do that. I'm not saying that you should run home and study them because I'll probably forget. But anyway,
You won't remind us.
you can remind me. Yeah, there you go. Okay. So if there are no further questions, I'll continue with the fundamental theorem of line integrals today. I think we can probably get out of here a little bit early anyway. Let's see. But don't let that stop you from asking questions. All right. Fundamental theorem of line integrals. Before we talk about the fundamental theorem of line integrals, I want to remind everybody what the fundamental theorem of calculus is. So recall from Calc 2, fundamental theorem of calculus, which says as follows. If f is an antiderivative of little f on AB, then the integral from a to b of little f dx, say, is capital F of b minus capital F of a. And in fact, while you may not realize it, this is essentially the heart of almost everything you did in Calculus 2, which is why it's called the fundamental theorem of calculus. Okay, what do I mean by that? Well, so what this theorem provides you is a method for computing an integral. And you all have internalized that method so deeply that you probably don't even think about it anymore. But when you're faced with this guy, there's a two-step process. One is to find this guy, and two is to plug in those values and subtract, right? That second part is really easy, but that first part is what you did all of Calc 2 on, right? U substitution, trig substitution, partial fractions, the list goes on and on, right? You memorized antiderivatives of trig functions, of polynomials, of exponential functions. I mean, right, that's what you did. You spent the whole semester in search of capital F, right? And this important theorem is really a vehicle that we use to compute integrals. And you're not going to be surprised to learn that, in fact, this fundamental theorem of line integrals is yet another vehicle that we'll use to compute line integrals. And there's a sort of a similar, another similarity. Sometimes you can't find capital F, right? What's a function where you can't find capital F? E to the x squared is the classic, absolutely. E to the x squared, you can't find capital F. This fundamental theorem of line integrals is going to have the same issue. There are going to be certain functions where you can't find this capital F. It's not capital F, but there's going to be certain functions where you simply can't find the right thing to go ahead and do the integral. Then you're stuck doing it the old-fashioned way. You got to parameterize and plug it in and yada yada yada, and it's much more difficult potentially. All right, so let's talk a little bit about how this works. First, I'll state the theorem. I'll use an acronym here, FT, Fundamental Theorem of Line Integrals, and hopefully that doesn't spell anything bad. If C is a nice curve, if C is a nice curve with from point A to point B, sorry, yeah, then the integral of f dot dr is equal to the integral of the gradient of little f is equal to little f of b minus little f of a. Okay, it has a lot of similarities to the fundamental theorem of calculus. Do you remember what this is? Gradient of f, it's the vector of partial derivatives, f sub x, f sub y, f sub z. Okay, so keep that in mind. This is a dot product, and then dr is precisely what you're used to. So playing the role of the vector field in this integral is the gradient of f. So if the vector field is the gradient of some function, then the fundamental theorem of line integrals applies, and it's really easy to compute the integral. You just take the function f of b minus f of a, and you're done. Doesn't matter. You don't have to parameterize it. You don't have to do any real work. Actually, I'm lying, but you have to do less work than you normally would. Okay, let's prove this, and then we'll move on and see how it's useful for computing line integrals. So the proof is very straightforward, and it follows from the fundamental theorem of calculus. Let's let r of t be a parameterization, x of t, y of t, z of t. And it's a parameterization such that r of 0 is equal to a, and r of 1 is equal to b. So there's nothing deep going on here. These are ideas that you've already explored on the most recent homework. You've got some starting point A, some ending point B. You've got some curve in space between these 2 points, and you've just parameterized it. So when I plug in t equals 0, I'm here. When I plug in t equals 1, I'm here. And as t goes from 0 to 1, I traverse the curve. Nothing new. So I'm going to let R be this parameterization of the curve C. I guess I should say somewhere parameterization of C. Okay, and here's the key observation. Let's look at f along the curve. So f of r of t, and take its derivative. So f along the curve means take x of t, y of t, and z of t and plug it into f. And I'm going to differentiate this thing. This requires the chain rule for multivariable calculus, which means I have to do f sub x, and I'm not going to write out all of the details here, but f sub x dx dt plus f sub y dy dt plus f sub z dz dt. And what I mean by details is secretly each of these functions, fx, fy, fz, are all evaluated at these. I just don't want to write all that out. Okay. Now we know that the gradient of f, so aside here, the gradient of f is equal to f sub x, f sub y, f sub z. So in fact, I can use that notation and the dot product notation to write the right-hand side like this, the gradient of f dotted with x prime, y prime, z prime. Does everybody see that? And x prime, y prime, z prime is secretly just r prime. Okay, it's at this point that I'm going to introduce an integral. So I'm going to rewrite the left-hand side like this, and now I'm going to integrate both sides from 0 to 1. Now, as complicated as the left-hand side looks, this is really just a fundamental theorem of calculus. Because what am I doing? I'm differentiating this thing with respect to t, and then I'm integrating it with respect to t. So what does that turn into? It turns into this thing evaluated here minus this thing evaluated here, right? Because I'm integrating a derivative. So the left-hand side becomes that, right? And the right-hand side is really just the definition of the line integral f dot dr. We're almost there. What's r of 1?
B.
B. And what's r of 0? And we're done. Okay, so just essentially using the fundamental theorem of calculus from Calc 2 and the chain rule from Calc 3 gets you this result. It's staggering the number of things that flow out of this observation. It really is. And I'm going to start with that today, and really the rest of the semester is the consequences of what flows out of this result. Okay, so let's start with some definitions here. What we want to do is we want to leverage the heck out of this result. So if F is a force field, or a vector field, and F can be written as the gradient of some little f, then F is a conservative vector field. And examples of conservative vector fields are like gravity and electric potential and fields that you encounter in nature are typically conservative fields. I'll talk a little bit more about where the word comes from in a second. This is not in the book, but it's certainly worth knowing. In this case, F is called a scalar potential, or just a potential. Okay, the key observation here, the key physical result is that the work done in a conservative field is independent of path. What do I mean by that? So I've got my pen here, and it has a certain amount of weight. And while I don't have to do a whole lot of work, I do have to do some work to take the pen from here up to here, right?
You could also bring that.
Yeah, so when it's just sitting here, I'm not doing any work, right? Because there's no distance traveled. But if I move a certain distance, then I've done work. If I go from here to here, is that positive or negative work? It's negative work, exactly, because I moved against the force of gravity. Okay, if I go from here to here, that's positive work. All right, so we're all kind of on board with that. Gravity, as I just mentioned, is a conservative force field. So whether I go from here to here, or I go from here to here, I've done the same amount of work. And that's what this is saying. So gravity, you're taking my word for it that gravity is a conservative field. But once you agree with that, or once you see that, then this result right here, right, here's the force of gravity. This is a work integral. And notice, what does this integral, the value of this integral depends on what? Where you start and where you end up. And it doesn't care how you got there. So I can go from here over to that corner and then back to here, and I've done the same amount of work as if I go from here to here. Okay. How is that possible? Like, how do we parse that? Well, the way to think about it is, as I go from here over to that corner, I'm going a lot further, and I'm doing positive work or negative work or what have you. But what happens is, along the way, it sort of all cancels except for the net change. Everything cancels except the net change. An immediate corollary to this independence of path result is the following. The work done around a closed path in a conservative field is 0. Okay, let's do a quick proof here. Let C be a closed path. What do I mean by closed path? The starting point and the ending points are equal. So the start point equals the end point. So let C be a closed path and F be a conservative field. And let's compute the work. So that's the work integral around this curve. Since F is conservative, we know that we can write it like this, right? And now we can apply the fundamental theorem of line integrals to write it like this. And we can say that this is 0 since what? Since A equals B.
So for any two vectors, you can add them and then use this theorem instead. Like for the problem that we had earlier, where it was like C1 and C2, you could add them first and then do the fundamental theorem. It'll be the same. As well as their vectors.
I'm not sure quite what you're getting at, but it sounds like you're not thinking about the force field at all. You're just adding vectors. I'm not sure. You've got to get the dot product with the force field in there somewhere. But anyway, there are definitely things. I'll try to talk about sort of more geometric approaches along the lines of the web work problem after I get through this stuff. Okay, so the work done around a closed path in a conservative vector field is 0. And that's a fairly standard kind of result in this area of mathematics. Let's see here. What I want to finish with, instead of a lot of theory, is I want to talk about the impact of this theorem on calculating line integrals. Okay, so if I'm staring a line integral in the face, right, this is typically what I'm faced with. I'm just looking at this line integral f dot dr. If I want to use the fundamental theorem, so if I want to use the fundamental theorem of line integrals, I first have to determine if f is conservative. And then 2, I have to find little f. So to use the fundamental theorem of line integrals to compute this integral, these are the 2 steps. If step 1 fails, then you can't use the fundamental theorem of line integrals. You have to use some other approach. You have to parameterize C and do it the long way. All right. So the first thing I'm going to do is talk about a test for conservativeness. And no, this is not a political election or anything like that, but there is an actual test. If you're handed a vector field, you can test this thing and figure out whether a little f actually exists, whether big F is conservative. So we're going to develop a test for this. So a test for conservativeness follows from a couple of astute observations and then Clairaut's theorem. Let's suppose first, let's let capital F, and let's do this in 2 dimensions first. It does work in 3 dimensions, but I want to keep it simple. Let's suppose F is the following vector field. It's PQ. And what do I mean by that? Well, if you look at some, for example, if you look at some of the exercises, right? Typically, you're handed a vector field that looks like that, right? And, for example, in number 4, what's P and what's Q? Cosine X and sine X and cosine Y. Here, 5P is Y, Q is 1 over X. So that's what I'm talking about, but I'm trying to keep it general. So I want to think about an F like that, P and Q. P and Q are just functions. And let's suppose that F is conservative. Then F is equal to the gradient of F, which is really F sub X, F sub Y. So we have F equaling 2 different expressions. We have F is equal to PQ, and we have F is equal to this vector F sub X, F sub Y. Then from this, it follows that P is secretly F sub X, and Q is secretly F sub Y. And Mr. Clairaut has something to say about this. What does he have to say about this? Py is equal to qx. Okay, so what we've just shown is if F is conservative, then Py equals qx. If F is conservative, then Py equals qx. This is almost a test for conservativeness. If Py does not equal qx, okay, let's go back to the book here. And let's talk about this guy. What's the derivative of P with respect to y here? 0. And what's the derivative of Q with respect to x? Py equals qx, right? Therefore, this is conservative, true or false?
No.
Py equals qx, therefore f is conservative. True or false?
False. Well,
False.
not potential.
It's the wrong way,
Yeah.
right? It might be true,
Yeah.
but it's not a theorem. It's not saying for sure, right? This is a test only if that relationship fails. If that relationship fails, then what can we say about f?
It's not.
It's not conservative. That's called the contrapositive. Okay, if P, then Q. If not Q, then not P. Okay, that's logic. Don't worry about it. Contrapositive. All right. It turns out, however, that in most cases, and I'm not going to prove this, in most cases, if Py equals Qx, then f is conservative. So we're going to take that as a fact in this class, and I'm not going to prove it. If you're really super interested in it, I will be teaching a class called Complex Analysis in the spring of 2014, where we will prove that over a period of about 2 or 3 days. Okay. Beautiful result, though. This is the test that we're going to use. And let me briefly walk you through the three-dimensional test. The 3D test is very similar. So let's say f is conservative, and we write f sub x, f sub y, f sub z. And on the other hand, we're going to say f is equal to p, comma q, comma r, like that. And instead of getting one relationship, Claro gives us 3 relationships that have to be satisfied. So we have P is equal to f sub x, Q is equal to f sub y, and R is equal to f sub z. So let me give you a couple and then see if you can come up with the last one. So Py has to equal Qx. Pz has to equal Rx, and there's one more.
Z has to equal R1.
Qz has to equal Ry. Those are the 3 relationships that have to be satisfied in order for this to work. Those are all the mixed partials, right? xy, xz, and yz, all the mixed partials. You've got to get those mixed partials to be equal. If these 3 equalities hold, then the same thing can be said. In most cases, f is conservative. In all of the cases that we'll encounter in this class, f will be conservative. I apologize for that ambiguity, but I just, yeah. Okay, let's do some problems here and then get you guys on the road. Let's look at 16.3.5. So I'm interested in 16.3.5. We want to find an f so that the gradient of f is equal to y cosine x sine x, or explain why there is no such f. What's going on here is you want to apply the test. This is a 2-dimensional vector, so you want to apply the simple test, py equals qx. If the test holds, then you have to find little f, which is what I'm going to talk about. If the test fails, you're done. You walk away. There is no little f. All right, let's walk through this. So capital F is y cosine x sine x. Okay, so identify P and Q, and then build Py and Qx. Py, what's Py? Cosine x. And what's Qx? Cosine x. So this is conservative. Now, the second part of this problem, now that we've determined that it is conservative, the second part of this problem is to find little f. And I'm not going to give you a set of instructions for this. This is best done by example. But once you watch this, make sure you practice this a few times, because especially when you're doing this in 3 dimensions, your head can really start to spin when you do this. So follow closely and do lots of these problems for homework. All right, here we go. We want to find little f. What do we know about little f? Well, we know that little f sub x is equal to what? Yep. So little f sub x is equal to p. And what's the goal here? The goal is to find little f. If I know f sub x, what's one way that I might figure out what little f is? I'm going to use the word anti-differentiate. It's a subtlety, but I'm going to use the word anti-differentiate instead of integrate. I could anti-differentiate with respect to x. So let's do that. So what is the antiderivative of this thing with respect to x? Y sine x. Is that the most general antiderivative? Plus c, good. Is that the most general c? Kind of. C of y. This is some unknown function of y. That's the most general antiderivative, because if I take the partial of this with respect to x, this turns into this, and what happens to that guy? It goes away. I have to be that general in order to successfully find capital F. Sorry, little f. Okay, I've used half of the information that's available to me. Let's start dealing with the other half of the information. So I take the derivative of this thing with respect to y. When it hits the first term, I get sine x. When it hits the second term, I get not a partial derivative, but in fact just a derivative of that second term. That's why I use the prime there instead of like a partial derivative kind of thing. Because there's only one variable in that guy, it's y. And so it's not a partial derivative, it's just a regular derivative. I know that fy is equal to sine x, right? And this often happens in these problems. You get some really nice cancellation. And what we learn is that c prime of y is equal to 0. What's that tell me about c of y?
It's a constant.
It's a constant. So I know that you knew that already, but you had to go through this step to get there, because sometimes there are going to be some situations where this actually doesn't happen. This does happen quite often in these textbook problems. But sometimes you'll get a function of y here, like a y sitting here. Then c would be y squared over 2 plus c. Something like that. Okay. But for now, we know it's just a constant. C of y is just a constant. So we've now determined little f. F is y sine x plus some constant k.
How come there isn't like a match for c of x? Couldn't you get like a function of x out if you started with q instead of starting with p?
Okay, so that's a really interesting observation. I started with f sub x, and then I found f, and then I differentiated with respect to y, et cetera, et cetera, et cetera. You can do all of this. In fact, I think it's a good exercise for you to try this. Instead of starting with f sub x, you could start with f sub y, and you'll end up at exactly the same place. It's kind of interesting.
But
You'll get the same result.
With c of x,
and then c prime of x, and then solve for that, and you're going to get the same function, even though it's ones of x and ones of y.
When you get to here, it'll be exactly the same. Yes. So that's a really great observation, though. Why did I start with f sub x? Because it doesn't matter, and so I just started there. But it's certainly worth convincing yourself that actually pans out. So I'll make that note here. If you start with f sub y, you get the same f. All right, so that's exercise 5. What I want to do now, in breaking with the tradition of the math professor always getting the easy problems, I'll do a hard one. Oops, I don't want to do that. So what I like to do now is 10, which has all the blood and guts and gristle involved with one of these guys. It's even three-dimensional. And finding little f in a three-dimensional problem, man, that can really get you going. All right. So the first thing we have to do, let's read number 10. So we've got this vector field, which is quite complicated, and you're asked to find the work done by this force field on an object that moves from 0, 0, 0 to 1, negative 1, 3. There's something conspicuous about this question, conspicuously absent. Not the gradient, conspicuously absent, at least with respect to section 2. They tell you where you're starting and where you're ending, but they don't tell you how you're getting there. Right? There's no path.
Well, it doesn't matter.
There's no
As
path.
long as it's,
Well, Ethan says it doesn't matter, but
it's conservative.
it might matter. When doesn't it matter? If it's conservative. So we hope that this thing is conservative, because if it's not conservative, you can't do the problem, because you don't know how you went from the origin out to this point. So this is a hint to test takers among you. When you're faced with the chapter 16 test and you see a question there, and I give a starting point and an ending point, but I don't talk about how I got there from one point to the other, strong hint that there's conservativeness stuff going on there. Okay? And if I do tell you what the path is explicitly, that doesn't mean that you should give up on the conservative route, but it's not a done deal. Because sometimes I'll give you the path, and you'll look at it and you'll say, hey, but this is conservative, so I don't care about this path, and I'll just go along. But if there's no path there, it's got to be conservative or you got nothing. Okay, let's talk about this, how to do this problem. We're trying to find the work done by this field as it moves from there to there. Okay, so let me write that down. This is 16.3.10, and we're trying to compute this guy. So first we'll test f, and I'll try to flip back and forth here and try to write this down. So we have e to the y, x e to the y. Plus sine z, y cosine z. All right, let me remind you what the test for conservativeness was in 3 dimensions. It was py equals qx, it was pz equals rx, and it was qz equals ry. All 3 of those guys have to hold. So let's start computing. Py is what? E to the y. Qx, e to the y. Good. Pz, 0. Rx, 0. Qz, cosine z. Ry, cosine z. So this is conservative.
Okay, now the fun. Okay, why am I doing this first of all? So we have this work integral, so we can do this by going a to b. Something like that, right? Okay. So we need to find f. And what we have to do is start going around and around and building these functions. So we know that f sub x is equal to e to the y, right? So let's find f. Okay, we anti-differentiate with respect to x. This e to the y is really just a constant. The integral of a constant, or the antiderivative of a constant with respect to x, is just x times that constant. Plus the most general constant of integration that we can muster, c of x comma, sorry, not x, y comma z. I will. So the most general constant that we can muster in this context is one that depends possibly on y and possibly on z. Now what? Let's do f sub y. So we do f sub y, and we get x e to the y. That's the derivative with respect to y. And now I'm using partial derivative notation because my constant depends on y and z. So I write c sub y. What does that have to equal? It has to equal this guy right here. And you get some cancellation. Now I have to find c. How do I find c? Anti-differentiate with respect to y. What's the most general constant of integration in that context? Some constant that depends on z. Why not x also?
So it show up.
Well, just remember the context that you're working on, right? We said that this depended on y and z, so I don't have to worry about throwing in extra x dependence. Okay. All right. So what we've now done is we've filled in even more of f. We've now found this part of f, and we found this part of f, and there's one little piece of f left to determine. And how are we going to finish this off? F sub z, right? So f sub z is 0 plus y cosine z plus d prime of z. And what does that have to equal? I've already forgotten. Y cosine z. And you get some nice cancellation there. And you see that d prime is equal to 0. Therefore, d of z is just some constant k. And this guy was just a constant all along. And f, final answer, is x e to the y plus y sine z plus some constant k. And I won't do it, but if you took the gradient of that f, then you would get the vector field capital F. Keep your wits about you when you're working through one of these. How do I finish this problem off? Let's go back and look at the problem. So I determined that f was conservative. I actually found the potential function, little f. What's left to do? Plug in this point, and subtract. Plug it into what?
F.
Little f, the potential function. Okay, so let's do that. And we're talking about 0, 0, 0, and 1, negative 1, 3. All right. Well, let's do this thing. X is 1 and y is -1 in the first term, so we get e to the -1. Y is -1 and z is 3, so we get minus sine of 3, it looks like. And a plus k. Minus, okay, now we plug in 0, we get 0 and 0 and k. And as will always happen, the k's cancel. And we get e to the -1 minus sine 3. The work done, moving from point A to point B, is this hideous monstrosity. I don't know if it's right or not. Let's dare I check?
Let's do it.
What is it? 16,310. 16,310. Yay. Okay. Any questions? You know where to find me 8 o'clock Sunday night. Have a good weekend.
What I was trying to say earlier was just that the path is independent, essentially, and that yeah. Right,